Hello everyone and welcome to Introduction to Signal Processing with Wolfram U. The title of this lesson is System Response. A system response is the signal that is observed at the output of a system in response to a non-zero input signal. So there is an input signal that goes through the system, and the output of the system as a function of time is called the system's response. In this lesson, we go over three classic system responses based on the type of the input signal. The list of input signals that we're interested in are impulse, step, and sinusoidal signals. When we study these system responses, it is convenient to set their initial conditions to 0 or assume that the system is at rest. When the system has 0 initial conditions, we say that the system is at rest. We will also study important parts of a system response, such as complementary and particular solutions that we had covered before. These parts are zero state and zero input system responses and transient and steady state responses. The impulse response of the system is the output of the system when the input signal is the impulse function delta t. To find the impulse response of the system, once we have the nth order differential equation that models the system, we solve that equation with input signal set to 0 and the initial conditions also set to 0 except for the highest derivative, which we set equal to 1. That is the n minus 1th derivative of y, as shown here. As we will see later, the impulse response of an LTI system is very important because it completely characterizes the LTI system that is initially at rest. This means that if we have an LTI system and we know its impulse response, then we can find its response to any other input signal. We will see this later in this course. For the first example in this lesson, let's find the impulse response of the system that is modeled with this differential equation shown here. We consider the homogeneous differential equation by setting x of t equal to 0 and setting the initial conditions as shown here. Y at 0 is 0 and y prime of 0 is 1. Let's use the Wolfram language to solve for the output signal y of t. This is the impulse response of the system, and plotting it, we can see how the impulse response changes over time. A sinusoidal signal that is multiplied by a decaying exponential that goes to 0 eventually as t goes to infinity. The next type of system responses based on the type of the input signal is the step response. This is simply the output of the system when the input signal is the step function ut. Here again, let's look at an example where a system is modeled by the differential equation given here, and we're interested in finding the step response of this system. To find the step response using the Wolfram language, we set x of t equal to the unit step function, and we set the initial conditions to 0, and we solve for y of t. If we plot the step response, we see that the output is 0 before time 0, and for positive values of t, it is a linear combination of two sinusoidal signals, and so we have these oscillations multiplied by a decaying exponential function. The oscillations die eventually, and the step response goes to the constant value 1 as t goes to infinity. For the case where the differential equation modeling the LTI system is a second-order differential equation with constant coefficients, in order to study a broad range of typical system responses, it is common to rewrite the differential equation in the parameterized form shown here. Here, omega n is called the natural frequency. Its value, which is a positive number, determines the time scale of the response. And psi is called the damping ratio, and it determines much of the character of the natural response. By natural response, we mean the system response when there are no external forces, when there is no input signal. Let's look at the step response of this second-order system shown here on the right-hand side by varying the values of the two parameters, natural frequency and damping ratio. The graph on the left side shows the location of the poles, or the roots of the characteristic equation of the system as a function of the changing parameters. The poles govern the stability of the system. For a system to be stable, all poles must lie in the left-hand side of the complex plane. For negative values of psi, the system is unstable. The response, as you see, is unbounded. It grows in time without bound. And also for larger values of natural frequency, we see that the amplitude grows faster in time. When psi is zero, poles are purely imaginary. They're on the vertical axis. Therefore, the system is called marginally stable. The response is a sinusoidal with constant amplitude. It oscillates indefinitely. It is bounded, but it has oscillation. So we call this system marginally stable. Also changing the frequency changes the time scale. Here, the period of the step response. When psi is positive, the system is stable. The poles are on the left side of the complex plane, as we mentioned before, and the step response decays exponentially to zero. But it decays differently for different positive values of psi. So we can break down this case where the system is stable into 3 cases with 3 different step responses. When psi is positive but less than 1, the response is underdamped. Most systems fall in this category. Poles have imaginary parts, which means we have oscillatory behavior in the natural response or sinusoid in the response, but also a decaying exponential. So it's oscillation with damping, which we call underdamped. For smaller values of psi, we have more oscillation in the response and less damping, and for larger values, there is less oscillation. Also, increasing the natural frequency increases the frequency of these oscillations. When psi is equal to 1, the response is called critically damped. Poles have real values which are negative. They're also equal. They are on the left side of the plane, so the system is stable. And there are no imaginary parts, so there is no oscillation in the response. Finally, the case where psi is greater than 1, poles are distinct on the negative real axis. We call the system, in this case, overdamped. The final type of system responses that we study in this lesson are sinusoidal responses. A sinusoidal response is simply the output of the system when the input signal is a sinusoidal function, let's say sine of omega t. As an example, let's find the sinusoidal response of the system modeled with the differential equation shown here. Using the Wolfram language, we set the input to sine of omega t and set the initial conditions to 0. If we plot the sinusoidal response that we obtained here together with the input signal sine of omega t, we see that changing the value of omega changes the amplitude of the output response. The sinusoidal response shown here illustrates a fundamental property of LTI systems, that a sinusoidal input results in a sinusoidal output with the same frequency. More formally, we say sinusoids are eigenfunctions of LTI systems. Eigenfunctions, if we recall from linear algebra, have the property that when we input them into the system, the output is the same function only multiplied by some scalar value. In the total solution of the differential equation modeling the system, we can look at these 2 parts of the solution. The zero input response, which is the output response when we have 0 input and non-zero values of the initial conditions, and the zero state response, which is the response when we assume 0 state or 0 initial conditions and non-zero input. The total solution then will be the sum of these 2 solutions. Let's find the 0 input and 0 state responses of the system described by this differential equation. Using the Wolfram language for the 0 input response, that is 0 input, non-zero initial conditions, we get a sine function multiplied by a decaying exponential. And keeping the non-zero input and setting initial conditions to 0 gives the 0 state response of the system. Let's plot these two components together with the total response, the sum of the two components, and we can see how each solution changes over time. The zero input signal goes to zero eventually. The zero state solution with unit step for the input signal goes to 1 after some time passes. And the total solution shown here in green is the sum of these two solutions. When we have an LTI system, the system response to some forcing function, which starts at time t0, for example, will have two components, transient response and steady state response. The transient response is the part of the response that will disappear over time if the system is stable. In other words, limit of YTR, where YTR denotes the transient response, as t goes to infinity is equal to 0. If the system is unstable, of course, the transient response could grow without bounds. The steady state response gives the long-term behavior of the system. It is the limit of the total response as t goes to infinity. Here, the steady state response is denoted by YSS. Let's find the transient response and the steady state response of the system shown here. Using the Wolfram language, we can solve the differential equation and get the total solution. Now, looking at the terms in the total solution, you can see that the parts that will go to 0 over time, which gives the transient response, are shown here. The parts with the decaying exponential. And the remaining terms make the steady state response. Plotting the two parts together, the total solution, we can see how the transient response oscillates at first and decays exponentially to go to 0 eventually. And the steady state response is a constant oscillation, a sinusoidal with constant amplitude. And the total response becomes the steady state response after some time passes, but in the beginning has some oscillations. To summarize, in this lesson, we categorized LTI system responses based on the type of input and learned about impulse response, step response, and sinusoidal response. We then looked at two different parts of the system response based on time duration or persistency, namely transient response and steady state response. The final category were based on the system parameters, input signal, and initial conditions. We gave the definition of zero state response and zero input response, and we went over some examples showing how to find these responses.